Hello guys, let's go on with our linear homogeneous recurrence relations with constant coefficients. Full mouthful, and this time I'm going to not with the previous time we did degree 2, now we're going to do arbitrary degree. I must say though, there's still something outstanding in degree 2 as well, but I want to do first a little bit more the general case, and then I will discuss what happens in degree 2 when you have the same root twice. Okay, so we are in arbitrary degree because the arbitrary degree case is almost the same as the quadratic case, apart from the fact that the calculations get much more complicated, and in fact so much more complicated that we cannot do many examples unless you use some more advanced tools like from linear algebra. We'll come to that. So what happens? Okay, we have in general now, and I'm going to do this again on an example. Let's look at the following example here. So we want to do the recurrence relation an equals 6an minus 1 minus 11an minus 2 plus 6an minus 3. So this has degree 3. I hope that everybody sees this now because we go back 3 steps. Not because there are 3 terms, because we go back 3 steps. Remember, sometimes it could be that a particular guy is hidden. For instance, that if this coefficient was 0, you would not see this guy. And there are only 2 non-zero terms, but it doesn't mean the degree is 2. The degree is always how far do I have to go back, not the number of terms. Don't get confused that. Okay. So that's degree 3. It's constant coefficients. Let's just very quickly go over. The coefficients obviously are constant. It's linear because these things are just on their own, not multiplied, not squared, nothing like that. It's homogeneous because there's nothing added here. And that's what we'll do in our next lecture, if that would be the case. All right, so we are exactly where we said we would be. What do we do? Well, it's kind of the same thing. We do again get a characteristic equation. So what is the characteristic equation here? Well, the characteristic equation is obtained in the same way as before by replacing an by r to the n. And then cancelling out the power of the highest power of r that you can factor out. The result of that is exactly as in the degree 2 case. So I'm not going to do this calculation with Rn, but you please do that if you want to convince yourself. This is exactly the calculation that I did for degree 2. But instead, let me go directly to what we should do. We start from the bottom. We know that we replace an minus 3 by r to the power 0, which of course is just 1. This by r to the power 1. This by r squared, and therefore this by r cubed. Okay. Notice that the numbers you get perhaps a little bit. You might get confused a little bit by these numbers, right? This 2 here, but there's 1 and there's 1 here. There's 2. It is because we start going up from the lowest, from the degree 3, so n minus 3. We go up by steps of 1, and the powers go up by step of 1. So our characteristic equation is r cubed is 6r squared minus 11r plus 1 because plus 6 times 1. Right, and then that's a degree 3 cubic equation, so we have to solve this. So that step 2 is solving this. But here is already the issue. It is not easy to solve higher degree equations. So this one, r cubed minus 6r squared plus 11r minus 6 equals 0. The only technique that you have learned, and actually the only technique that is really available, is factoring. But it is not obvious how to factor a degree 3 equation. There are formulas for degree 3, but they are very, very complicated. And Google them and you'll see it's not something you even want to use. Even if you have the time for it, it's awful. It contains many square roots, and it's really not a nice formula. Even if it gets worse in degree 4, there's still an equation, which is even more difficult. But then in degree 5, something very strange happens. There are no solutions in general anymore. There are no ways, no methods of solving this in general anymore. Of course, there are solutions, but there are no ways. We cannot solve them in an algebraic way. And that's not because we're stupid or perhaps 2,000 years in the future they can do this. No, they will never be able to do this because one can show that no mathematical method can produce always the solutions in an exact fashion. And that is something that has been done by a very young guy, Galois. He was 18 years old when he proved this, and he didn't live much longer because for some, in his youthly passion, he got enthralled in an affair with a girl, and that led to a duel in which he got shot. Those things happened in those days. This is in the 19th century. So that was by Galois, who actually had just luckily, for us, had proven that we cannot solve this in degree 5. But even in degree 3, it's a difference between possible and practical. In degree 3, it gets already very difficult. What are our options then? Well, sometimes the only options we really have in this case is looking for divisors of the constant term and trying those as possible roots. So in this case, that would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Quite a lot of things to try. And first of all, that is because if there are nice roots, now that's not necessarily mean that's the only way of solving it, because there could be roots that are irrational numbers or even complex numbers, and then this method would not work. Even this works only if there are nice numbers, and more correctly, if there are integer solutions. So in this case, okay, we could try for roots like 1, for instance, or minus 1. But if I already plug in 1, I'm lucky here, right? Because plugging 1 is actually somehow the easiest of all things, so let's always try that first. That's 1 minus 6 plus 11 minus 6. That's actually 0. So we see by trial and error, we find that r equals 1 is a solution. Now, I repeat, the trial and error method you should only try it when you have a divisor of this constant term, and 1 is a divisor. So that's good news, because we know then that r minus 1 can be factored out, and then so we know that this third degree can be factored in an r minus 1 and a quadratic. How do you find this quotient here? Well, you do long division. Now, that's awful, and I don't want to spend time on that, so please go look it up if you don't do anymore how you do. It's not awful, sorry, I didn't mean to say that, but it's something, a calculation that you have to do. The reason that I don't like to do it for you is because I have learned it one way, and the European way, and you guys do it the American, or most of you have done it the American way, not all of you, but most of you. And they are slightly different methods, and I get always confused with the method, so I'm going to just tell you what the result of this factoring is. The result is that this would be r squared minus 5r plus 6. So please trust me that this is correct what I said. Now that is good news, because a quadratic I know how, well, in principle, yeah, I know how to factor, because worst case scenario is I have the quadratic formula. Remember, this has happened once already in one of the examples when the Fibonacci sequence. So do not dismiss this method. But in most cases, you're just going to factor very simply here, and we see two numbers that multiply to 6 and add up to 5, minus 2 and minus 3. Do this. So we have now the three factors, and this gives me r is 1, r is 2, and r is 3. Okay, that's somehow still very similar to the quadratic case. Well, the next step is also similar. Propose a solution. Now, how did we do it then? We said, okay, we took, in the quadratic case, we had two roots. We took those roots as basis of the exponential function. Well, now we have three roots and do the same. Of course, now there gives three possibilities, and therefore three constants. Alpha, 1 to the power n, plus beta, 2 to the power n, this 2, this was the one that I used there, and now as a third term with this 3 as basis, and the next letter in the Greek alphabet is gamma to the power 3n. Okay, of course, 1 to the n is not really anything, so let me quickly simplify this a little bit as this. So this is how a general solution look like. Be careful, right? Again, do not simplify things by putting this as 2 beta to the power n. It is beta times 2 to the n, gamma times 3 to the n. And then for step 4 is again the same, again. So everything is really the same, as I said, only the calculations get more complicated. So what we do now, we have 3 initial conditions. I did not give them yet, that was my bad, sorry about that. The initial conditions, so the initial conditions, it is an example from the book, so there they were stated there. And so A0 is 2, A1 is 5, and A2 is 15. I should say that in principle, these initial conditions can be any numbers, right? And so those have there's no restriction on what these initial conditions are. But each initial condition will give me exactly one solution. Okay, so let's I have them right there. So A0 is 2, and we know already by putting a 0 is very simple, that is just taking the sum of these alpha, beta, and gamma. A1 is equal to, that was 5, and so now I have power 1, so alpha plus 2 beta plus 3 gamma, and then finally A2, that was 15. 15 is alpha plus, now I have to put in, this is a little bit, the numbers get a little bit bigger here, right? What is going on here with my, n is 2. So we get 4, sorry, this, my pen is not really, let me go out this and go in, sorry, sometimes it helps. So plus 4 beta plus this squared, that is 9 gamma. But what happens now is we have 3 equations with 3 unknowns. Some of you have seen this, but this was kind of an optional material in 1275, so you might not exactly know how to do this, but we need it now. So I'm gonna, if you don't remember anymore how to do it, it's basically the same as the degree 2 case, but it's just more work. And it's very often better here to use the elimination method, because from the elimination you can get into a system of 2 equations with 2 unknowns, which you then can solve either whichever way you want. So the elimination method is what it tries to do is tries to use one equation and get rid of, for instance, in this case, I would like to use, the simplest thing for me is to use alpha. Alpha here, I think so I want to use alpha to add or subtract a certain amount my equation to the other equations, that the alphas in the other equations disappear. So in this particular case, this would be I'm thinking of subtracting here and this, both this equation from those equations. So if I do this, if we call this 1, 2, and 3. Sorry, so I do 2 minus 1, that is the equation. So I subtract now, so I get alpha minus alpha, that is 0. 2 beta minus beta, that is beta. 3 gamma minus gamma is 2 gamma. And sorry, I have to do this here too, so 5 minus 2 is 3. Now I do 3 minus 1. So if this was 15, right? So 15 minus 2, that's 13. Let me write it this side now. And now I subtract again, alpha minus alpha, that is 0. 4 beta minus beta, that is 3 beta. And 9 gamma plus gamma is 8 gamma. So this is easier. Now I can, for instance, solve in this guy. Beta is 3 minus 2 gamma, and then plug it in. So then we have 3 times 3 minus 2 gamma plus 8 gamma equals 13. That is 9 minus 6 gamma plus 8 gamma is 13. Okay, and that gives me, bring the 9 to the other side, that would make it 4. And then this is 2 gamma. And so I see that gamma is 2. And once I know what gamma is, I can plug it in here and see that beta is negative 1. And once I know that, I can plug it in, say, for instance, in here and see that 2 is alpha minus 1 plus 2. So I see that alpha is 1. Let me double check here that I did this correctly. 1 minus 1 and 2, yes, okay. So the solution, therefore, is an is alpha was 1, and that was, right, so we go here, we have 1 plus that was negative 1, so minus. I think my pen is dying, guys, and I don't want to interrupt the talk here. If that happens, then I might stop and make a part 2. I'm just going to charge it a little bit. So you now plug in 1, minus 1 and 2. Since my pen is, I'm trying to charge it while I'm talking, so you get the solution that you then find in the textbook. All right. So that's the case of degree 3 or higher, but very important here is that we dealing with 3 different roots, or in general with all different roots. So now comes the question, what if some root is there twice? In particular, the quadratic case where we had sometimes double roots. So I want to do one of the quadratics first, where we have a double root. That would be the equation. So I'll do this example here. Okay, I don't know what is going on with my pen. Let me try one more time to get out, in and out here. Reset my pen. No, my pen is dying. Let me see here what my pen is. What? No, it's 34%, so it's not that. Okay, then if it's not that, then let's try again. Okay. Yes, okay, so the equation that I want to the recurrence relation I want to look at, an equals 6an minus 1 minus 9an minus 2, initial conditions, again, because it's quadratic, right, constant terms, non-homogeneous, etc., etc. A0 is 1 and A1 is 6. Good. Step 1. Correct the equation, r squared equals 6r minus 9. That's r squared minus 6r plus 9. We have to factor that, so I'm doing step 2 already, okay. But the two numbers that do this are twice the same number, minus 3 minus 3. That's what I was talking about, a double root here. The number of times a root occurs in the solution is called the multiplicity. So this is so 3 is r is 3 has multiplicity. Why is my pen acting up? Sorry, let me see. Multiplicity equals 2. The number of times, in other words, if you would write this in a compact form, you would write this as r minus 3 squared. Okay, so for instance, I'm going to come back to the question, but if you have more generally, suppose you have a recurrence relation and it looks something like this after your factor. What are the multiplicities? So 3 would have multiplicity 2, 1 would have multiplicity 5, and minus 4 would have multiplicity 1, because there's only power 1 for that. Okay, and that's important for what I'm going to say next, but I'm going to not do very general cases like this. So let's go back to this case here. So what do we do in this case? Well, the problem is in the next step, right? Why can we not just do whatever we do? Well, look at what I would do. As I would say, an is, now I propose, you take the roots and take the 3 to the power n. Right? The geometric series with basis 3, that would be one solution. And then another solution would be, well, there is no other solution because it would be again 3 to the power n. And that doesn't make sense to look at alpha times 3n plus beta 3n. Well, that you can combine that into one constant, right? So what's the next possibility? And this is what happens. This is the new part, is that if you have multiplicity 2, then the next possible solution will of the form n times 3 to the n. So I'm claiming that we have now two these are true solutions of this recurrence relation, and I will verify that for you, okay? But before I verify it, let's see what we would do with them. Now that we know it, let's assume that you trust me, that is the case. What we do? Well, we do then what we always do. We say, okay, we take alpha times this plus beta times this, because if I take a sum or any multiple or any linear combination of these solutions, that will be again a solution. So step 4 now is, once I have, this is the step where kind of we do something else. Everything else is the same except that step 2 was more difficult. Sorry, step 2 was not more difficult, but in step 3 is where we do something else. So what is step 4 now? Now that's the same thing. You know the initial conditions. So what are the initial conditions? A0 was 1, so that means alpha plus, but now be careful. Now we're plugging in n equals 0 in here. So we're going to put n equals 0. You notice that the next term, the second term, completely disappears. So I was writing something there where it should not have been there. Sorry. Okay, sorry. I'm pointing to the wrong thing here. So that's just alpha. And then A1, now I plug in 1 in this equation. So here I put in n equals 1 everywhere. That gives me 3 alpha plus beta times 1 times 3. So 3 beta. Okay, so this is now much easier to solve because I know already that alpha is 1. A1, what was A1? 6, right? That was 6. And so now I have to just plug in. So that is 6 is 3 plus 3 beta. And I hope you see that it means that beta is actually also 1 in this case, not just a coincidence. So we see that our solution is 3 to the n plus n times 3 to the n. Now you might not be convinced and say, okay, for 3 to the n, remember that this was the case, r to the n. If it's a solution of the stochastic equation, then we know that that geometric series is a solution. But why is n 3 to the n a solution? And that's, by the way, not in general the case. If you have a root of your characteristic equation, let's say 3, then n times 3 to the n is not a solution. Look at here. This I have to, yes, look at here. We had 1 was a root, 2 was a root, and 3 was a root. Yeah, 1, 2, and 3, but there was no n here. You see, in the general solution that we eventually found, which I never wrote down because my pen was dying. Okay, now that my pen is back to life, let's try to write it up in 1 plus minus 2 to the n plus 2 times 3 to the power n. You notice that there are no n's there. There's nothing of this form. Okay, so. But let's now double check that is actually I claimed that this was a solution of my recurrence relation. The only problem, by the way, why are we still going on? If I have a solution, why don't we stop? Remember, this is always because of the initial conditions. This particular solution might not satisfy the initial conditions. It doesn't. But let me show you that it was a solution. So let's look at the recurrence relation here. So I have to plug in and this number in there and see that fits. N to the power 3n is the same as 6 times. Now replace n by n minus 1. So that would be n minus 1, 3 to the n minus 1, minus 9 times. And what would happen here? The index is now n minus 2, so n minus 2 times 3 to the power n minus 2. Well, let's work all this out. That would be 6n times 3 to the n minus 1 minus 6 3 to the n minus 1 minus 9n times 3 to the n minus 2 plus 18 3 to the n minus 2, right? I'm just expanding these two guys. Okay, so, okay. It looks different, right? It doesn't look that the left-hand side is equal to right-hand side, but that is because there are different powers of 3. Let's try to get everywhere a power of 3 to the power n. You might say, how are you going to do that? Well, I can always borrow powers of 3, right? This contains a power of 3. I write this as 2 times 3, and then I can multiply this 3 with this 3 to the n minus 1, it becomes, so I can multiply this 3 with this 3 to the n, it becomes 3 to the power n. So this would, what I get is 3 to the power n. If I use these two guys, and what's left is then 2n. Okay, let me do it one more time here. So 2 times 3, combine these two, that would be 3 to the n, and I have minus 2 left. Here we have 3 squared. And I can combine this with this guy to get, again, 3 to the power n. And what is left is this n. So minus n, 3 to the power n. Here we have 2 times 3 squared. Let's combine this to get plus 2, 3 to the power n. Let's see what we get now. Now we have like terms. Everything is powers of n. First of all, these two guys cancel out. And what do we have here? We have 2n minus n. So that is 2n minus n, 3 to the power n. That is n, 3 to the power n. But that's exactly what I'm claiming it had to be. So you see it works out. Okay, now this is what happens for a quadratic. I'll give you homework problems. But the same thing happens, can you do for, let's say, I'll do one example here that I've taken from the book. I'll do this one here. Let's look at this recurrence relation. an is equal to minus 3n minus 1 minus 3n minus 2 minus an minus 3. So degree is 3, right? Because we have to go 3 back. The characteristic equation, let's try to write it down right away, is minus 3r squared minus 3r minus 1. So if I bring this on the side, it's 3r squared plus 3r cubed plus 3r squared plus 3r plus 1. Now I know my formulas, so I know that this is actually r plus 1 to the power 3. It's the binomial expansion for third power. You might not remember this anymore, but okay, if you try to find another way. Notice that this means, what does this mean? This means that this minus 1 is a root with multiplicity 3. What's the multiplicity here? Well, that's this index, right? This exponent, 3. So minus 1 is root with multiplicity 3. Notice that minus 1 is a root. If I plug in minus 1, this would be, this term gives minus 1, this gives plus 3, this gives minus 3, and this gives plus 1, that cancels out. And once I have a root, remember I know that r minus that root, so r plus 1, is a factor, and I can do long division, and I see what is left, and if you do it that way, you'll see that eventually you get to r plus 1 cube. So, what is now, so step 3 here, what's the solution look like? So what do we do now? Okay, so so far we had something with a root of multiplicity 2. By the way, so now we have something with multiplicity 3. So we know that it's minus 1 to the power n. We always take the root as the base of our geometric series, but I cannot take 3 times the same thing because that doesn't give me anything new. So I already know that I can multiply with n. Well, I can also multiply with n squared here. So in general, how does it work? So in general, so let's go to this example that I had. I don't know where I had erased it. Here is, no. I erased that example. So again, let's go back. So suppose that we have our characteristic equation. Suppose it is of the form r minus 2 to the power 3, r minus 5 squared, r minus 4. How do we find now the general solution? First of all, what's the degree here? Well, the degree of the recurrence relation, I haven't given it a recurrence relation, but I could do that, is the same as the degree of the characteristic equation, so this is 6, degree 6. Okay. what is the general solution look like? Well, we have this 2 here, right? So one of the roots is 2, but it has multiplicity equals 3. So what do we do then? Let me give myself a little bit more space here. Well, we take this power 2 to the n, we have to do it 3 times, and what we do is we have a degree 1, degree 0, degree n, and here we have an n square. Okay, so let me, okay, sorry. I'm going to change the problem a little bit and make this into a 5 here. So the degree is now 10. Okay, to see a little bit what happens in higher powers. We're never going to do this, but just so you know what happens. So this would be alpha plus beta plus gamma. Sometimes one then prefers to write this factor out to 2n. So alpha plus beta n plus gamma n squared times 2 to the power n. Okay, what happens for 5? Well, in 5 we would have 2 powers, 5 to the n. 5 is multiplicity 2, so we have 5 to the n, and we have 5 to the n times n. So here we would have, let's go on with our Greek alphabet, delta and epsilon. So again, if I would combine this, I would have combined this. And then finally, what happens here? So r is 4 with multiplicity 5. So we would have here, so I'm going to write it, okay, let's see what I can squeeze this in here. So we would have here, I'm not going to be able to squeeze this in, sorry. Yeah, okay. I would here have 5 powers of 4. This is 4, right? So we'd have 4 to the n, 4 to the n, 4 to the n, 4 to the n, and 4 to the n. And each would come with a higher power of n. So here we would have nothing. So here we would just multiply n. Here we would with 1. Here we would multiply with n. So here we would do n squared. Here we would get n cubed. And here we would have n to the 4th. And then we would have to put general coefficients. I'm running out of, I don't remember the Greek alphabet completely, so I'm going to just write random Greek letters here. So that will be rho plus sigma plus tau plus theta plus zeta. Okay, so this gets a little bit ugly. Let's gather what we have. Rho plus sigma n plus tau n squared plus theta n cubed plus zeta n to the 4th. Now, don't get thrown off too much by these Greek letters, but let me now quickly wrap this up and say what is going on here. This has degree 3, and so what's the general solution look like? A degree 2 polynomial, 1 less than 3, times the root to the power n. This root, 5, had degree 2, so we have 5 to the n times a polynomial of degree 1 less than the multiplicity. This root 4, therefore we can have 4 to the n, is now multiplied with a polynomial of what degree? Well, multiplicity is 5, so degree is 4. So a general polynomial of degree 4. And general means that we still have to determine what each of these coefficients are. Now, if you want to call them A1, A2, A3 or something like that, be my guest. Right? In the book they use double indices, which I hate because I always get confused by them. But it's very impractical to solve this thing. So I just wanted to show you how it looks like in general. You'll never be able to actually solve these things unless you use a computer program or programming MATLAB or something like that, which we don't do in this course, remember? Okay, let's go back now, therefore, to the case at hand, where we have only one solution of multiplicity 3. That is a special case, that can happen. And then we have the general coefficients plus gamma. So minus 1 to the power n is actually a rather simple thing. So what we get is alpha plus beta n plus gamma n squared. Oh, not be careful, it looks almost like, okay, sorry, plus gamma n squared times minus 1 to the power n. Now this minus 1 to the power n is a rather harmless thing, right? Because what it's going to do, it is just going to flip the sign. But so the main thing is this alpha, beta, and gamma. So how to define them? That's again the same. That's initial condition. In some sense, these initial conditions get a little bit simpler because of the n's there's going to be some more cancellations, especially in if A0. So A0 was, again, I forgot to tell you what the initial conditions were. According to the example of the book was A0 is 1, A1 is -2, and A2 is -1. I could take different numbers. I just don't want to take arbitrary numbers because then I get fractions and I don't want you to scare you off already more than I'm scaring you off now. All right, so A0 was 1, and that means that I'm plugging in this equation n equals 0. That's nice because everything goes, that's just an alpha. So I already know what alpha is. Okay, A1, that was -2. And so if I plug in now I plug in n equals 1 in this equation, I get alpha plus beta plus gamma to the power, well, times -1. Don't forget that there's a -1 to the n there. And then A2, that is equal to -1. And that is, and now I plug in n equals 2 in here. Alpha plus 2 beta plus 4 gamma times -1 to the power 2, that's just 1. Okay, so alpha is 1. I can plug that in this equation. So the next equation is -2 is, remember there's a -1 here. So this minus alpha, which is 1, minus beta minus gamma. I'm expanding the minus sign. Or perhaps it might be more confusing to do that. So I'm going to actually be smart and say I'm doing this. And let's multiply both sides with -1, then there's no negative signs anymore. Okay, so what I'm left with, so this equation now is, remember alpha is 1, right? So 2 is equal to 1 plus beta plus gamma, and the next equation is -1 is equal to 1 plus 2 beta plus 4 gamma. So this means that beta plus gamma is equal to -1, no, to 1. Okay, and this means that 2 beta plus 4 gamma is equal to -2. Okay, and now you can use again whatever method you want, elimination or substitution. I like substitution here, so beta is 1 minus gamma. If I plug this in here, I get 2 times 1 minus gamma plus 4 gamma is 2. That's 2 minus 2 gamma plus 4 gamma is 2. The 2's cancel, right? Yeah, so I find that gamma is 0. Is that really what I want? Let me see here. No, I must have made a mistake somewhere. What do I do wrong? No, I made a mistake. What did I do? 2 minus 2 gamma plus 4 gamma is -2, right? Yeah, -2. Oops, -2. Right. I'm not saying it was impossible, but I looked at the example before and I didn't remember that there was a 0 there. So it is a -2 there. So if I bring this now to the other side, so let's see, we have here 2 gamma equals -4. So I see that gamma is -2. And if I plug it in here, then I see that beta is 1 minus -2, beta is 3, and I know already that alpha is 1. So the general solution is an is this polynomial 1 plus 3n minus 2n squared times -1 to the power n. Okay, that's correct. Okay, so that's how this works with higher degrees and also with multiple roots. But you can see that I basically reached already the limit of what we can calculate really, because if you would have to deal with degree 4, you would have 4 equations in determining these alpha, betas, and gammas, and then delta. You would have 4 equations, 4 unknowns. You can do this actually, and some of you know how to do this if you have taken linear algebra. But if you don't know linear algebra, it gets really awful to try to solve that. And plus, it's still very time-consuming. So I'm never gonna ask you something like that. So the degree 3, that is still feasible, right? So I want you to be able to do those. Okay, so I'm gonna assign homeworks. And so what we're gonna do next is, what now if we have non-homogeneous equations? And what this means is you'll see that we're gonna have to use what we just learned in this section in the previous lecture, because we're gonna first solve the homogeneous part, so we're ignoring that non-homogeneous part, and then we're gonna deal with that non-homogeneous part. So in other words, what comes next, be sure to know how we do these things. To do the non-homogeneous case, we need to know how to do the homogeneous case. That's my point here, that make sure that you understand this before you go to the next lecture. Okay.